Welcome to this new video on capacity spectrum method. This method will enable you to find the performance point and correspondingly displacement, which is known as the design displacement or target displacement. The method is intimately related to pushover analysis, so I've taken it as a part 3 of the pushover analysis. Capacity spectrum method was first given in ATC 40 in 1996. So we start from the more basic concept which we discussed earlier in other video, response spectrum. Response spectrum is a graphical plot between time period and peak response quantity, displacement, velocity or acceleration of an S-DOF system with a given damping under a given ground motion. So why this is taken? Because the design spectrum that we are going to discuss here again and again is derived from the response spectrum. Design spectrum is the smoothened average response spectrum of several earthquakes in a particular area. So a typical earthquake and its response spectrum is shown here. The design spectrum is also known as demand diagram because it gives the demand imposed on the building for which it has to be designed. So demand curve is taken from one code, is like this. It is Indian code. This demand code, which is given in the code, is given at 5% damping. 5% damping is the material damping for RCC. So this is taken as the basic damping in which the design spectrum are given in different codes, and this is the elastic condition of this system, elastic condition of the demand. So this is called 5% damped elastic demand curve. Now damage happens in the buildings or structures, and because of this the period of the building will increase and it will increase the damping in the system. Because of the higher damping, response will be reduced, and all the more the demand in the system will be reduced. Demand in the building is imposed by the earthquake, which is represented by the design spectrum in the code, a level. So this demand that is imposed on the building depends on its dynamic characteristics like time period, flexibility, etc., and the shaking level to which it is subjected. So demand reduces, so what happens to the design spectrum given in the code? It will be now lower, a design spectrum which is called reduced demand curve or reduced demand spectrum. The meeting point of capacity curve and demand curve, what is this? Now your demand curve typically in different codes are given in terms of period in the x-axis and SA by G or SA in the vertical axis. So this is your original 5% damped demand spectrum, and due to damage it has got reduced up to this level. The point where the capacity curve and the demand curve meet indicates the point where capacity and demand or the reduced demand in the system are equal. This is optimum design point and is known as performance point. So where it will be equal, let us see. We have drawn the demand diagram or the design spectrum on the left side and the capacity curve or the pushover curve on the right hand side. So if they meet, then they have to be plotted on the same diagram. So we plot it here. So this is my reduced demand diagram as shown in the left side figure, the lower design diagram. They are meeting at this point. So this is your performance point. What is the magic of this point? Here the capacity of the system is given up to here this much, and the demand imposed on this, reduced demand imposed on this, is also at the same point. So what happens now? You have designed a building which is optimum because the capacity and the demand are equal. There is no wastage of material and there is no also lack of safety. So we need to find this performance point, and the displacement corresponding to this on the x-axis here is the target displacement or design displacement. Now problem is the axis values are not same in both the cases of the design diagram, design spectrum and the capacity curve. Here it is time period versus SA by G. Here it is roof displacement versus base shear. So they are not identical, so this cannot be done directly. Let us see how we can convert this to a system where both the curves can be plotted on the same ordinate values. So this conversion of the normal design spectrum and normal capacity curve to acceleration demand response spectrum is called the ADRS format. It was given by ATC 14 1996. So the steps involved are conversion of the time period to spectral displacement given by this expression. Then conversion of base shear to spectral acceleration given by this expression. And conversion of root displacement to spectral displacement is given by this expression. So here Ti is the time period for any ith step, because you have to get so many points and finally get the curve. So I is the variable which indicates different points. SAI is the spectral acceleration at ith step. G is acceleration due to gravity. BI is the shear force at that step. W is the seismic weight. Alpha 1 is modal mass coefficient. Delta roof is the roof displacement. PF1 is the participation factor for mode 1. Phi 1 roof is the modal coefficient for the first mode at the roof level. So alpha 1 and PF1 are defined here. The expression for PF1 and alpha 1 are given by these simple expressions, which involve the weight, the motion coefficient in the first mode, and the number of stories, number of degrees of freedom in the system n. Now let us see the conversion to ADRS format. You should be clear, we are converting the design diagram to ADRS format and the capacity curve or pushover curve to the ADRS format. So we have taken the pushover curve here, which is between roof displacement and base shear, and we have taken the demand diagram or the design spectrum, which is between the time period and spectral acceleration or spectral acceleration ratio. It is to be converted to a system where it is in a common coordinate system. So we take spectral displacement on the x-axis and spectral acceleration on the y-axis and plot both the demand diagram and capacity diagram. Their shape does not change after the conversion, so they will look like this. Now how to convert, we have discussed in the previous slide the formulae. We are showing it here pictorially again. This base shear is to be converted to spectral acceleration here. So this is the formula which will convert it to spectral acceleration. This base shear at any point will be converted to spectral acceleration at that point. Then the roof displacement to be converted to SD. So this is the formula using participation factor for first mode and the mode shape coefficient for first mode at the roof level. And here time period is to be converted to SD. So this is the formula. Any time period will be converted to SD through this formula. These formulae were first suggested by Mehani in 1993. So we have converted our capacity curve and the demand curve to a common plot between SD and SA. Let us further see, this is the initial 5% elastic demand line given in the code, and we have taken it between SD and SA. This is reduced demand. The demand reduced, we discussed earlier, due to the damage, the demand on the system will be reduced. And we have drawn the capacity curve on the same plot between SD and SA. So this point where they are meeting is the performance point. And the displacement from the origin up to the performance point is called the target displacement or design displacement, which we shall be using again and again in our design of structures in coming videos. Now there will be performance levels of the structures which can be shown in the pushover curve. So when the damage is very less after the elastic current, there are a little damage, it is the immediate occupancy condition. More damage, well, but the life is not threatened is the life safety performance level. And the system is almost on the point of collapse but has not collapsed is the collapse prevention CP performance level. In between IO and LS, there are points where also your structure may lie. So this is called damage control range. And between LS and CP also you have so many levels, discrete levels, or you can say continuous levels. This is called limited safety range. So you can have a building in the limited safety range or also in the damage control range. If they are falling exactly to those discrete points IOLSCP, then those will be called as IOLSCP buildings. However, suppose a building lies in the damage control range somewhere here. What is the name of the building? This will also be called as, lying here will be called as SCP building. Now there is a point called the yield point. It is a consensus point obtained through a graphical method where the system is said to have yielded. So for the drawing or getting the yield point, we draw a tangent to the starting of the capacity curve, and then we have already decided our performance point. This can be decided as a trial, considering that we are designing the system for a damage condition here. For example, I can design it for LS level or CP level, then those will be corresponding point here. So this point I have decided, and draw a line on the backward side from this performance point, line BC. So line OA and BC are touching at this point. This is your yield point. Now while drawing this line, we have to see that the area of the curve above this line CV and area of the curve below this line CA and the bounded by the capacity curve, these two areas, this black area and this yellowish area, this should be equal, so that energy is not lost in our process of conversion. So this is the yield point here. It has the yield displacement dy. We are not writing SDY for the sake of simplicity. We are simply writing dy for yield displacement, d for displacement, and on this side base shear is by. So here immediately we are not showing in the SA format but in the base shear format. So this is your by, yield displacement at the yield point. Now you are having another point here which is at the level of 0.6 by. So get the yield point, you have to observe three things here. Area that is below this curve and above the straight line shown by blue color, and area shown by the yellowish color here should be equal. Also your tangent should pass through the point 0.6 by, where by you are selecting at yield point. So satisfying all this condition, you get the yield point. And the displacement at the performance point is your dp, and acceleration corresponding to the ap, though still it is in the base shear format. If it is converted to acceleration format, then we shall call it as ap. We have taken another slide where we have already shown the target point or the selected target point pp, and we have got the yield point by the process we have discussed just now. So we have dy and ay at the yield point and dp and ap at the performance point. So these are the points, yield point and performance point, shown by the displacement and acceleration values. Now when you convert the demand diagram to reduced demand diagram, how do you convert? The reduced demand depends on the dampings in the system, and damping depends on the damage. So based on the damage, you have to decide that once you have decided the damping chi, if it is in percentage, then you can this formula R equal to 10 divided by 5 plus chi in percentage. This is the reduction factor by which you will multiply the ordinates of the original 5% damped elastic design diagram to get the reduced demand diagram. It is more precisely given here. The spectral acceleration, the ordinate at any percentage chi or damping chi percent, is given by 10 divided by 5 plus chi percent multiplied by the ordinate of the original 5% damped elastic spectrum. So you remember this formula, we shall be utilizing this again. Now computation of the total damping. In the previous slide we have seen the chi is to be calculated, then you can get the reduction factor, and then you can get the reduced diagram. So question arises how to get the damping out of the damage. So this is discussed here. From dynamics we know this expression. Hysteretic damping is given by this formula 1 by 4 pi Ed by ESO. It is the energy dissipated in the hysteresis, and ESO is the strain energy stored in the system. So we have taken a plot between ST and SA, and this is our target point we have selected. So your pushover curve is coming here, and then if you allow it to go in the reverse direction, then it goes like this and again goes like this, and this is your hysteretic curve. The area under the hysteretic curve gives you the energy dissipated in the hysteresis process. So to get the area, we draw a parallelogram here. How it is drawn? This is the performance point, and here will be the yield point. So this way we get this line, then other lines are parallel to this. The strain energy is from the origin to the maximum point, that is target point, whatever distance is. If we take this as the base and this height as the altitude, then yes, we will have base into altitude, the area of this green diagram. And ED is the area under this hysteresis loop, which is also equal to the area under the parallelogram shown here. And total damping, effective damping, is the material damping plus hysteretic damping. Hysteretic damping will derive now through this process, and material damping is already known to us. For concrete it is 5%, and for steel structure it is 2%. So we have taken this same parallelogram again here, which is ABCD. We want to get the area of the ABCD so that we get the ED, the energy dissipated in the hysteresis. We take another small parallelogram here from the using the yield point, performance point, and the curve drawn parallel to this, which was obtained when getting the yield point. So this dotted curve is parallel to this, and this line, dotted line, and these lines are parallel. So we get this parallelogram OECF. If you can get the area of the OECF and multiply it by 4 times, we get the area of the bigger diagram ABCD. So we want to get this area in terms of the yield point coordinates and performance point coordinates. So this is your AY DY point, yield point, and this is your performance point DPAP point. Now we take this parallelogram OECF in a new diagram in a bigger scale. So it is OECF, same parallelogram here, and we draw a rectangle touching the performance point and making it a rectangle here like this. Now if we look at the rectangle, taking the rectangle, we have taken extra area beyond this original parallelogram, which are A1 here, which is equal to A1 at the bottom, A2 triangle here, which is equal to the A2 triangle here, and A3 triangle shown by bluish color at the top, and A3 triangle shown by the bluish color at the bottom. So if we take the area of the parallelogram, which is nothing but equal to distance OG, which is equal to DP, and distance GC, which is equal to AP, because this is your performance point. And all the areas A1, A2, A3 can be expressed in terms of the yield displacement point values dy ay, and the performance point value coordinate dp ap. So this ed equal to 4 times this rectangle minus this 2 times this a1 a2 a3, because a1 a2 a3 are occurring twice. A1 is given by this expression, a2 by this expression. These are coming from the geometry, very simple. A3 is given by this expression because A3 is a rectangular area, so one distance is another distance. So if you simplify this expression given at the top, you get this expression ed equal to 4 times ay dp minus dy ap, which is very simple and easy to remember also. So hysteretic damping formula 1 by 4 pi ed by ESO, where ESO equal to half ap dp. If you put here, you get the expression of the hysteretic damping rising out of the hysteresis in the system, or the pushover curve generation. And total damping only material plus hysteretic damping. Now this is shown elaborated here. We have our demand diagram. Demand diagram in certain courses are starting as horizontal line from the beginning, and in some course it is starting but inclined line and then horizontal. Anyway, these are all the same. And we have the capacity curve here shown by the pink color, and the reduced demand line shown by the dotted line. Intersection point is the performance point, and through the process also you have got the yield point somewhere. which is not shown here. So dy ay is also known in the process. So you know the reduction factor given by the formula we have discussed, where xi is the total damping you have calculated, xi m plus xi h. If you put all the expressions of the previous slides, you get this effective damping given material damping, which is 0.05 for concrete, and this expression which involves only ay dy ap dp, which we have already calculated. So this gives the effective damping, and again these are given numerically here. At 5% no damage because the elastic condition, so reaction factor is 1. 10% is 0.78, 20% is 0.55, and so on for other cases given. Remember that we have considered only hysteretic damping and material damping, but in some cases there can be some added damping in terms of added damping devices. So in that case that will be added up and that will form the effective damping. Total damping in systems may not be so high like 40%, it may be around maximum 20-25% in practical cases. So with multiplying the ordinates of the 5% damped elastic diagram, you get the reduced demand diagram. When the ordinates of demand diagram are multiplied by the reduction factor corresponding to the damage state, we get the reduced demand in the system. So 5% damped demand diagram, and the capacity curve is shown here. This is the trial performance point, and we have decided through bilinearization we have decided the yield point. So dy ay ap dp ap are known, and all the formula we have discussed are repeated here. Ed is given by this, ESO given by this, hysteretic damping is given by this, total damping is given by this, and the reduced spectral acceleration for the reduced demand diagram are given through this expression. So you can easily get the reduced demand diagram, and wherever they are touching this capacity curve and reduced demand curve is your performance point. Now I have taken the diagram from ATC 40 for the sake of explanation. This is the elastic demand diagram, and after reduction this middle diagram was obtained. After further reduction this lowest demand diagram was obtained, which is finally touching the capacity diagram shown here. So you get the performance point somewhere here. In this diagram you can see the lines, radial lines from the origin are given, t equal to half second, t equal to 1 second here, and so on. So this is in SDSA or ADRS format. The question is why the radial lines from the origin should give time period at constant time period lines. So this is explained here. We have the expression for SD given as t square SA g by 4 pi square. In the earlier expression we had used I here for the ith point. I is removed here to give a generalized expression for this. So this can be expressed in terms of SA, taking SA on the left hand side. So SA equal to 4 pi square by gt square into SD. If time is kept constant, then this whole the terms within parentheses become constant. So it equal to y equal to mx pattern, a straight line passing through the origin. That's why when t is constant, you get a straight line passing through the origin. So these are the radial lines showing some value of the time period lines. So capacity spectrum method, let us further explain. In the previous slide of the ATC 40, we have shown the reduced demand diagram is gradually going towards downside. But it may not be so. Depending on the performance point you select, it may go on the upper side also and it may go on the downside also with respect to the previous one. So we have considered this is the demand diagram. This is the capacity diagram, capacity curve, and we have decided that we shall design system for this much damage. So this is my trial performance point number 1, and through bilinearization of the system I got the first yield point YP1. So I know the DY1, AY1, DP1, AP1 this way. Now you get your reduction factor and get this reduced demand diagram, which is I am showing as reduced demand diagram number 1. Intersection of the reduced demand diagram and capacity curve gives you this point, which is performance point 2. This was trial, we have given number 1, so this new one is performance point number 2. Now the assumed PP1 point and obtained PP2 point are widely apart here. So obviously our initial assumption was not correct, so we want to correct it further. For that purpose, we shall take another trial performance point in between these two. So we can take a performance point P3 in between these two, and corresponding to this, by bilinearization of the curve, I get the yield point 2, YP2, and so those values of dP2, or rather yes, dP2, dy2, ay2 and dP3, ay3 are known. So knowing this, I get the reduction factor and get the next demand diagram, which is demand diagram number 2. So demand diagram 2 has gone above the demand diagram, reduced demand diagram 1, because of our selection of the performance point, trial performance point. Now whether we are satisfied or not, the second reduced diagram is going through this, so performance point is here, and your selected performance point was PP3 just nearby. So if you are satisfied that they are very close to each other, you can stop here, or you can make one more iteration in this similar process. So let us make a summary of what we have learned. Capacity spectrum method gives us the performance point and hence the design displacement or target displacement. Capacity spectrum method is an easy and appealing method explaining the procedure graphically and visually. Because it is visual, it is easy to understand what is happening inside. Of course, for buildings and structures, you need not do it personally by hand. This will be done by the software you are using. Capacity spectrum method demonstrates how the damage affects damping and hence response of the structure, and also demand imposed on the structure. All these are very clear through capacity spectrum method. I have shown here some pushover curves for 4-story building of some building. So this performance point is here shown by a black rectangle, IO is shown by circle, LS is shown by small triangle, and CP is shown by star. So since performance point is here before the IO point, so this is IO building, because building is in the IO range, and this pushover curve is to be given in short direction and long direction. In long direction also you have to check whether it is in the IO or not. Yes, the IO is here and performance point is here, so it is IO building. Another building is taken which is 10-story high, and here also we see the performance point is here and IO point is here, so it is IO building. And in the long direction also, it is just near the IO point on the left side, so performance point is here, so it is IO building. So this I have taken from a real building designed by me. Here I have shown the hinges formed on the buildings. So hinges have some colors, and those colors will show you the performance levels. So this color here, pink color, is the IO performance level, building was IO. These hinges will be formed in the pushover analysis and also in the time history analysis. The diagram below shows the interstory drift diagram. This we have not discussed so far. When we discuss the time history analysis, we shall take this topic, interstory drift. So this is story 1, story 2, story 3, story 4. At the story 1, the drift is this much up to the maximum point. For story 2, the drift is this much, and story 3, drift is this much, and story 4 this much. So this can be written also like a straight line, but this is the common way of showing the drifts. You are getting so many lines because drifts have been shown under many earthquakes. Each earthquake is giving different drift diagram, so that is what is shown here. Thank you very much for coming out me up to here. Please subscribe the channel, like and share the videos, and put your comments so that we can discuss further on this. Thank you.